So, in the last lecture I had shown you how to calculate given the CPM network and then given the durations of each activity which we denote by Tij. Then I had shown you how to calculate the early starts of nodes and late starts, right. So, you remember that calculation, and then I had also shown you that once you come to the finish point, then of course, we take the late finish also here as same as early start. So, for this node it will be 30-30, and so for example, and then you can trace back the critical path. I showed you that also. So, here for example, for node 7 both the early start and late starts are same, because this is a critical activity, and then this way we go on. So, therefore, I told you that to compute the critical path you just have to see how this calculation came about, or this calculation came about. So, for whichever activity the early start or late start got calculated, that will constitute the one of the critical activities. So, then your critical path actually came out to be. So, this was your critical path, right, and then 4, 5, this is 2, 7, because you see each of them has the same early start and late start are the same. So, this was your critical path. I showed you this calculation. Of course, the network I have chosen is little different from what we had last time. Okay. Then I also said that you see the nodes are events. For example, if you look at node 4, then it tells you that this is the completion of activities 1, 4 and 2, 4. Right. And of course, 1, 4 and 2, 4 cannot begin, like for example, 1, 4 cannot begin till 1, 2 is S1 is complete, and similarly 2, 4 cannot begin till S2 has been completed. So, in a sense node 4 indicates the completion of all these 4 activities. So, nodes represent events. Okay. And so, then we computed the early start and late starts. For example, this tells you that you must not be here later than 7, because it is a later start, because if you delay the point this number here, then the other activities, the following the successive activities will get delayed. So, these are events, but and so the critical path we showed you, but the manager also needs to know the early start, late starts of activities, because he has to concentrate, he or she has to concentrate on the completion of all the activities of the projects. So, we need some more tools for the manager to be able to manage the project properly, and so we will define this. For example, ECIJ is the early completion time. Okay, sorry, completion time of activity I j, right, and this would be E I, that means early start of node I, because the activity I j will begin at node I. So, the early start of node I plus the completion time of the activity I j. So, this will give you the early completion time of activity I j, and similarly you want to compute the late start of activity I j. So, that will be late start of activity I j, which will be L j. So, because j denotes the completion of activity I j. So, late start completion of or late reaching of node at node j minus T I j. So, that will give you the late start, and you can immediately see that now you can have this concept of slack for each activity, because the manager needs to know which are the activities which have slack, and so maybe you can the manager need not concentrate so much on the activities which have slack, but has to concentrate on activities which have no slack or comparatively less slack than the others. So, this is a kind of tool that the manager needs, and so here we will define. Okay. So, if you want to just get a feeling for these numbers, then for example, I am computing this here. I am saying that the early completion time of activity S1 will be early start plus the duration 2. So, this is ECIJ, right, and similarly the late start would be L1 minus 2, because L1 is the S1. So, L1 is 4, and then this minus the that is what I am defining the T I j, L j minus T I j. So, this would be 4 minus 2, which will be 2. So, the two things should be the. So, this will be therefore, the activity S1 can actually begin on the after the second day. See, here we are saying that S1, because of this activity, S1 this number is E1 is ES is 0. right. But when you look at the early start of or late start of activity S1, it can begin after the second day, because its duration is 2 days. So, therefore, it will still be over on the 4th day, and so this activity can begin, right. This will not get delayed. This is the idea. What I am trying to say. So, therefore, you need to know these numbers also. So, here LSIJ is 2, and you see then we define the slack. Slack is Lj minus ECIJ, that means the late completion or late time for node j minus the early completion, or late start of activity ij minus the early start, right. So, therefore, this would be, say for example, here you see this would be, if you subtract these two numbers or you subtract this. So, 4 minus 2 and 2 minus 0, that is your slack. And if you want, this is a good check for you, if you want to make sure that your calculations are correct here, then this is a good check, that this number should be equal to this number, and that gives you the slack for each of the activities, and this is a very useful tool for the manager. So, you can check for some more activities. For example, if you want to look at 1-3, 1-3, this difference is 3 and this difference is also 3, right. And you want to look at the early start for activity 1-3. So, this is 1-3, right, and we said that early start plus the duration, right. Early start plus duration, which is 6. So, that is 6, right. And then you want to look at, so this for 1-3 we are looking at. So, this is 6, and then late start would be 5, because here the L3 is 9. So, 9 minus 4 would give you 5, right, which is different from this here. So, for example, activity 1-3 can actually begin after the 5th day, right, and so on. So, and then of course, you check the numbers, 5 minus 2 is 3 and 9 minus 6 is 3. So, this gives you a feeling, a little more feeling about which activities to concentrate on and which can be slackened a little bit, so that the manager can use all his energies and so on in trying to see that the project gets completed on time. Okay. Now, of course, one can also I did not think that it was really necessary to go into it, but anyway I will just define this term for you. See, you can fine tune the slack, because there is also this concept of free slack, which is the amount of time by which an activity can be delayed without disturbing the early start of all its immediate successors. So, which would be something like you can look at the slacks for each. Okay. So, of course, defining this would require a little more effort and so on, but one can look at it while you are reading some more literature. But anyway, so you can fine tune this concept of slack time, and there is something like free slack, because the manager may also not want to delay the early start of certain activities. So, then the immediate predecessor, the amount of slack that you can use for that particular activity should be is equal to the free slack. So, these are these concepts. Okay. Now, another computation that I wanted to another point I wanted to make was, see here when we made these computations, I took the due date to be 30 days. For example, for this particular project, the project is ending on the 30th day. So, then I took it to be the due date also, but it is possible that the due date may be different from the project completion date. And so, if your due date, which we denote by D, is greater than your LT, which is also equal to ET in our calculation, right, then you see project with number D will be bigger than 30. So, then there will be a slack for each of the critical activities also, because if this is more than 30, this will be more than 24 and so on. So, the slack will percolate, or the difference between the due date and this number, that will percolate to all the critical activities also, and of course, for the other activities also the slack will go up by that amount. So, that is a happy situation, because the manager then has even slack time for critical activities also. But in case the due date is less than your project finish time, then you see there will be negative slack, and then there is more cause for tension and so on. So, anyway, you can still talk of slack being negative, it is possible, right, but obviously, the manager cannot, for example, for this project, the manager cannot in any way complete the project before the 30th day. Right. So, if your due date is less than 30, then there will be some penalty or something, but then even then the manager would try to see that the project does not get delayed beyond this number, because then the penalty will increase. And of course, and in the next lecture I will talk to you about project crashing, and I will show you that with one can try to reduce the duration of a project by using more resources and capital to expedite certain activities. So, that part I will discuss later on with you. So, then one can also handle the case when the due date is less than your LT, that can also be possible. The next question that comes is that is it possible that if you add more resources, for example, you put in more labor, you have more, you bring in more equipment and so on, whatever it is, can you try to shorten the project? And of course, shortening the project would mean that you are going to spend more money, because you will hire more labor, you will use more resources, whatever you are using. And so, the question becomes that, but then if the project takes a long time, like if you can shorten the duration, see, associated with the duration of the project, there are other indirect costs, I will explain in a minute. So, then the question arises, is there an optimal duration of the project? So, I will talk about it in a minute, but here, for example, as I said, that you can, if you the linear programming formulation can also be, linear programming formulation would be here, if you say that UI is the completion time of, UI is the variable associated with node I, right, that is and denotes it's denotes the time of its occurrence. That means, when will this, for example, when will this event take place? That is, when will all these 4 activities get completed? So, UI is the variable associated with node I and denotes the time of its occurrence. So, then what do you want to? So, here, yeah, you want to find out. Let us say, because US we will always take as 0. So, you want to find out minimize UT subject to. So, now here the thing is that you will write UI plus Tij less than or equal to Uj, where Tij denotes the, so Tij is the time for activity, time taken by activity Ij, or the job Ij, job, activity, whatever you want to call it, subject to UI plus Tij less than or equal to Uj. So, here this will take care of this thing. For example, when you want to look at node 4, then see the corresponding constraints here will be what? Just for node 4, I want to write down for you. So, here this will be that U1 plus 3 is less than or equal to U4, but you will also have this constraint to say that U2 plus 3 is less than or equal to U4. So, you see, it will take care by itself. So, for example, here this cannot start. See, this one, if you look at this node, it will be 2 plus 3 5, but this one is 4 plus 3 7. So, your U4 should not be less than 7, and these two constraints together will take care of the fact that U4 will satisfy this, and so this is a reasonable. But you saw that we really do not need the linear programming method of solution, because the network is acyclic, and so a simple labeling procedure gave you the labels, UIs that you require by just going along and labeling the nodes, right. So, this is what it is, and now let me talk to you about the crashing. So, this is what we call network crashing. So, I will work out the, I mean, I try to give you what are the issues involved, and then we try to come out with a method for finding the optimum duration of the project. So, let us continue with network crashing. So, what I am saying here is that project cost is of two types. Okay, this is a direct cost and indirect cost. So, as I was suggesting earlier, direct cost would be the cost associated with a particular activity. That means the number of the amount of labor and other resources, whatever machinery you require, that is specific to a job, right. And the indirect cost is actually the cost related with the whole project, because you may hire premises, you may hire managerial skills, you might subcontract and so on. The subcontracts will certainly, because if you subcontract certain jobs, then they will come under the direct cost for a particular activity, but the indirect cost will be basically the cost related to the whole project, which you then divide, because the project the indirect cost will be related with the duration of the project. And the idea here, and so what we are suggesting is that, see, if the activity takes place at its normal, so this is, sorry, this is not cost, this is normal time. If an activity takes place, gets completed in its normal time, then the cost involved, the direct cost would not be as high compared to the cost when it actually gets completed during its crash time. So, that means there will be certain time associated with an activity to which, I mean, the time you can actually try to complete the activity within that time, but certainly you cannot reduce it further than the crash time. So, you cannot complete the activity in time less than the crash time, and normal time is the normal. So, you have some concept of what resources, what labor and other things you would require to complete the job, and so this is this. And the indirect cost, of course, because the if you complete the activity an earlier time, then the direct cost would be less, sorry, in crash time, then the direct cost would be less, and the direct cost. So, the indirect cost starts increasing with the duration of the project, and the direct cost gets reduced when the project time gets delayed, right. So, you have to think of, you have to come up with the duration of the project, which is the best trade off between direct cost and the indirect cost, right. So, when you have these, this is a very simple presentation of the cost, and then you see your total cost. So, this is your total cost curve, right. This is your total cost curve, and the minimum will rise somewhere here between the crash time and normal time for each activity, and then of course, you will add up and find out for the whole project what is the optimum duration of the project. Okay. So, these are the two costs involved, and you can yes. So, the managerial skills are required to really find out what would be the what would be the how would you compute the costs for each activity, and then of course, the cost of the indirect costs. These figures are most of the time available, because the activities are deterministic in nature, and so you know what all is needed and so on. Okay. So, then yes. So, now we have this diagram, and then we can first try to formulate this problem as a linear programming formulation. Okay, I would call it linear programming formulation if I do not have the integer requirements for Tij, the completion time. If it can be treated as a continuous variable, fine. If it's if the requirement is in terms of if the Tijs are required to be integers, then it will certainly be integer linear programming problem. Okay, so here now we are going to define Cij as the crash as the if you are given the crash cost for the activity and the normal cost, the difference, because crash cost will be higher than the normal cost, and then normal time, normal duration of the activity, and the crash time. So, the difference. So, this ratio will give you the rate of. So, this we will say slope or rate of crashing. Okay, so this will be the rate of crashing for each activity I j. Once we have this, then I can and let me denote this time by a I j. Sorry, this let me this denote this by b I j, because I have yeah. Oh no, this is b a I j. Okay, because t I j is greater than or equal to a I j. This is a I j. A I j. Okay. So, the crash time we denote by a I j for activity I j, and this is b I j, the normal time, right. So, therefore, if I define this rate of crashing of activity I j by c I j, then if the actual t I j is the variable denoting the actual duration, because now that I am going to crash the activities, I do not know what the actual completion time for each activity will be. So, this is what we want to find out through this linear programming formulation, where we want to minimize the total cost. Okay. So, this would be T I j is the actual duration, and since B I j is the normal one. So, you have crashed the activity by this many days, and so this into C I j will give you the cost of crashing the activity I j, right. And then if you have U t minus U s, you can treat this as 0. So, then U t minus U s, so t is the completion time of the project. Okay. So, suppose I want to say that I want to minimize the cost, given that I want to complete the project in time less than or equal to t, right. So, this is U t minus U s less than or equal to t, and then the usual constraint, the linear programming constraint, that your U j must be greater than or equal to U i plus T I j or I j, and then your T I j should lie between A I j and B I j, because the duration you don't want to go beyond normal time of the normal completion time, and this you cannot go beyond this also on the left. Now, here this objective function you can write as, because this is a constant, so I can write this as okay, I will write this as max summation C I j T I j. Okay. So, because minus of C I j T I j, so that becomes max, and that constant is I mean, we can just keep it aside, fine. And then see, if this is a maximization problem, then my constraints are less kind, fine. And here I will write this constraint as, so this come on the top, that T I j minus T I j is less than minus A I j, right. The constraint was T I j greater than or equal to A I j, I multiply by minus sign, this is what it becomes, right. Now, just out of academic interest, since we have whenever we have talked of a linear programming formulation, we have also looked at its dual, and I just want to show you, even though we will not use this particular formulation here, but anyway, this is of interest in the sort of academic interest, right. So, I am trying to write the dual to this LPP formulation, and you see that your right hand side, of course. So, we will associate the variable v with this constraint, and of course, t is your completion time of the project, then x I j with these constraints, and alpha I j beta I j with these two sets of constraints. So, then if you want to write the dual, you see the objective function will be T v, right. Then you have only with respect to these, because this is 0. So, minus A I j alpha I j summation this, and beta I j b I j summation this, right. That is your objective function, and the constraints you see, if you they should look familiar, because these are your flow constraints. Remember, for the max flow and min cost flow problems we have written down, and you see the dual, but you can also check for yourself. For example, for U s, see U s is appearing here. So, therefore, that is a v there, because it will be minus v. So, I have shifted it to that side, and then how else will U s appear, because this is I j. So, for example, you have like this, suppose you have a j 1, j 2. So, I will just explain for one. So, then you see you have constraints like U s minus u j 1 less than or equal to T s j 1, right, U s minus. So, you will have x s j, because the corresponding variable will be s j 1. So, you will have x s j 1, x excess j 2, excess j 3. So, here you will have summation this, and then of course, this appeared with a minus sign. So, here of course, this is the only constraint in which it will appear. So, that this will be 0, and so this will be v. So, minus v, which goes here, right, because associated with this it is minus v, I shift it to this side, right. For all other nodes, this thing it will be, you can see that I j. So, for arcs going out of a node, you will add up the x I j's, and for arcs coming into node I, you will subtract. The usual constraints we have been handling, right. So, this will be 0 for I not equal to t comma s, and similarly, here it will be v plus sign. So, when I shift it to this side, it becomes minus v. So, for I equal to t, your constraint of course will be minus this, because these will not be there, and minus this wherever whichever nodes are connected to t. So, you, for example, here you have t. So, you will have like this, and for these arcs it will be minus sign. So, this summation will be equal to minus v for I equal to t, and then you have the last column with respect to t I j's. So, the column here would be see this will be x I j, then minus alpha I j and minus beta I j, plus beta I j, sorry. For this it is plus beta I j, right. And since there we do not have any sign constraints on t I j, remember we have made all these explicit constraints, the non-negativity constraints on t I j's. So, therefore, the corresponding this constraint will be equality here, and here also we are no restrictions on the signs of u i's, and therefore, though of course, when you start with your u s as 0, all other u i's will also be positive. So, but we are not mentioning the constraints explicitly. So, therefore, all these constraints are as equality, right. And now, we just can simplify the so, anyway, these constraints show you that there is a flow going out of, I mean, you can look upon V as a flow which is going out of node V, and it is reaching node T, and the other nodes act as transshipment points. So, these constraints are definitely your flow constraints. Now, this constraint I can simplify and make it in an implicit manner, and what I will do is, see, if x I j is less than C I j, then you can put alpha I j equal to 0, because then beta I j being non-negative, this sum can make up for C I j. I can just dispense with alpha I j and put it equal to 0. In that case, my b I j will become C I j minus x I j, which is non-negative, right. Similarly, if x I j is greater than or equal to C I j, then I will put b I j equal to 0, right, because this will act as a surplus variable. And then I will define alpha I j as x I j minus C I j, which is also non-negative, because x I j, right. And then the objective function for the dual, see, now I can remove my alpha I j beta I j. So, you see I have taken care of this constraint already, and so then I will substitute for alpha I j. Alpha I j is x I j minus C I j, right. So, this is minus a I j, this is x I j minus C I j, right here, and then plus b I j C I j minus x I j, and you can look at this constraint. So, you see here the objective function therefore, is not a linear function completely, it is a piecewise linear as we call it, and you can see from here that see, yes, because for x I j less than C I j, your slope is minus b I j, and here the slope is minus a I j for x I j greater than C I j, right. This is this, and which is valid, because you have a I j less than or equal to b I j. So, this implies minus a I j is greater than minus b I j, and tan theta is an increasing function, right. So, therefore, this slope would be, so you have minus a I j greater than minus b I. So, the corresponding angle will be bigger, right, because tan is an increasing function even though they are negative. Is it okay? So, this is the idea. So, therefore, the objective function for the dual problem is a piecewise linear function, and we can solve this problem as a min cost flow problem, right, where, and we have already learned the methods. So, my idea is to show you that see, trying to show you that where all you can get these kind of formulations that we have studied under the banner of linear programming, and how versatile the simplex algorithm is, because you can use it anywhere. Of course, it is possible that you may have some better algorithms for solving this problem, but you see that it can be formulated as a min cost flow problem. Okay. Except that the objective function is not linear, and we have methods available for handling piecewise linear functions, because all you have to take care is the moment your x I j is becoming bigger than C I j, then you have to take this as the cost coefficient, and for x I j less than C I j you have to. So, a small modification in your current network simplex algorithm that we did, you can handle this situation also. So, you can solve this problem this way, but of course, I will give you a more direct method in the next lecture. Okay. Now, just try to look at this also. See here, for example, if your completion time of the project is given to be very large, in that case, this constraint will always be satisfied, will never be satisfied as equality if your t is large. In that case, your v will be 0. Right. And so, what it means is that you can look upon V actually, because V is not the flow in the network, but when you look at the dual, we are treating it as a flow value, but what it will say is that V will be 0. That means, you do not need to spend any money on having extra resources to shorten the project duration, because it is anyway very large. Right. But if t is very small and this constraint is it's not even feasible. That means, this number, because when the UIs you compute, they come out, they satisfy these constraints, but this constraint is not satisfied, and that means the primal is infeasible, and therefore, the dual would be unbounded. That means, any amount of money that you spend in trying to shorten the project would not help you, because anyway you cannot meet the current t value. So, by shortening t, you will again earn whatever money you spend, you will not be able to complete the project in that time. So, this is the kind of interpretation. Again, the idea was that you see what meanings the dual variables can acquire, and they can give you an understanding of the problem. So, this was the idea behind my, even though I know that we will not be solving this problem in this way, but I still wanted to show you the how far the applications of linear programming problems can go. Yes, and now here, so I think that tells you that the crashing of the network project and finding out the optimal duration can be formulated as a linear programming problem. But here again, and I have shown you the dual, which is an interesting problem by itself, but again there are ad hoc methods which are faster, because as I said that in case you require your Tij's to be integer valued, then of course, we have not learned the techniques for handling such problems, and also solving integer programming problems is not a very happy situation, because the things get complicated. So, we have fortunately nice ad hoc method which will also give you optimal solution, and so I will like to discuss. But because this is a linear programming and its extension course, I thought I should show you the limitations of linear programming also, because it always helps to be able to exploit the structure of the problem. And this is, and so as you saw that when finding out the critical path, because the underlying network was acyclic, we could with a simple labeling technique find out the longest path on the critical path. So, we did not need the linear programming formulation, and here also we can formulate the problem as a linear programming problem, but we will not do it, because we will exploit the structure of the problem and find out and come up with a faster method for computing the optimal duration of the project. So, I will indicate that through a simple algorithm and give you the method. So, to show you how network crashing is done or duration of the project, I will go through the procedure by showing you these steps through an example. So, this is here the example that I have written down. So, network flow problem, and I have given you the see this cost and this time. So, this is also for normal. normal duration. When the normal duration of the projects, for example, for project 1, for the job 1 2 activity 1 2, and so the normal cost is in thousands of rupees. So, okay, this is the cost. So, this is 4,000 rupees is the normal cost for the activity 1 2. Then the normal time taken to complete the activity would be 6 days. This is in days, and then this will be crash. Okay, I could have written here crash cost. So, this is crash cost in thousands of rupees again. So, to crash the activity by 1 day or total, okay, to reduce the time from 6 days to 3 days for activity 1 2, the cost of crashing it into 3 days would be 5.2 thousand. Okay. This is how we are going to read it. So, for example, what I have done is here, this is the normal time, this is the crash time. So, 3 days you can crash the activity by 3 days, and the difference in the cost is 1200. So, you can so that means 1200 divided by 3, which is 400 rupees. So, here I have written the rate of crashing the activity by 1 day. So, that is this is the rate of crashing. Similarly, you can verify that for job 1 3, the rate of crashing per day is 500, because here the cost is 3 and here this is 5. So, 2000 is the total cost of crashing, and this is from 5 to 1. So, 4 days you can crash the activity by 4 days, and therefore, the cost of crashing per day would be 2000 divided by 4, which is 5000. So, you can understand the data given here, and as we see that the critical path I have already pointed out to you. I mean, this is the example we discussed earlier. So, 1 2 2 4 4 6 and 6 7. Okay. So, this is your critical path, and the total duration is 26 days. The near critical path is 2 days away, which is, so the path is 1 3 4 6 7, and its duration is 24 days. Now, total normal cost, if you just add up, that means if you do not crash any activity, then this adds up to 31,000, and then the overhead cost that we said, the indirect cost is rupees 3,000 per day. That means, if you reduce the project duration by 1 day, then you save rupees 3,000 in terms of indirect cost, right. So, you have to now balance the cost of crashing and the which will of course increase the cost, but then since you are reducing the duration of the project, the overhead cost will come down, right. So, this is what we are going to do. So, first let me just outline the algorithm, and this is, as we formulated the problem as a linear programming problem, but I want to now show you that because your network is very simple, we can use an ad hoc method to get to an optimal solution, and this is where you can see that optimization is not simply applying an algorithm to a problem, it is also trying to see what is the structure of the problem, and if you can exploit it in some way, or if you can use some other information to get to an optimal solution, you should do it. So, therefore, let me just give you this ad hoc algorithm that we call it, but it gets you the optimal solution also. So, first what we will do is identify, this is identify the critical activities. So, which will currently our critical path is 1 2 4 6 7. So, these activities 1 2 2 4 4 6 6 7 are the critical activities. Then we will select the activity with least rate of crashing. So, out of these 1 2 3 4 4 activities, I will select the one which has the least rate of crashing, and then I would have to determine the number of days by which this activity can be crashed, which means that, see, this will be have to be the number of days by which the particular activity I have selected here can be crashed, and the number of days by which the next critical path is away, because if I crash this to whatever number number of days I can crash this activity, but in the meantime some other path becomes critical which is longer, then it does not help me to reduce the project duration, right. So, the idea here is that I should be able to reduce the project duration by crashing a particular activity. Okay. So, here for example, if you look at 1 2 can be crashed by 3 days, right, which means that I can, if I crash the activity 1 2 to its crash time of 3 days, this path length will become 23, but then the next critical path is 24 days. So, that means my project duration will not come down to 23 days. This is the whole idea. So, this is important, you have to always choose the minimum of the two numbers. So, then once you decide by how much the activity can be crashed, then we will update the network, that which means that you can somewhere note down as to what the current duration of the particular activity which you have crashed. You have to note it somewhere, and then you can also compute the improvement in the cost, the reduction in the cost, right. Then continue till some other path becomes critical. So, we will continue doing this 2 and 3 till some other path becomes critical. And of course, here I should have mentioned that since you are looking for an optimum duration, you will also check that you will decide to crash an activity as long as the crashing cost is less than the overhead cost, because you want to cut down on the cost also, right. So, that part I have not added here, but certainly you will keep doing that. So, then continue till some other path becomes critical, and then after if there is more than one path that is critical, then you see you will have to combine, you will have to crash all the paths which are critical simultaneously, right, to be able to reduce the project duration. So, to do that you will have to pick up on combination of jobs. That means, you will have to identify the combination of jobs on the on all the critical paths. So, that by crashing that set of jobs or that combination of jobs, you can reduce the project duration. So, once we do that, then again I will apply the same rule that I used here. I will select the set of activities which can which has the least rate of, you will add up the rates of crashing the activities in a particular combination, and you will select the one which has the smallest rate of crashing. So, same thing you will continue, and of course, you will to obtain the optimal duration, crash till the cost of crashing is less than or equal to the, again I am not writing it very precisely, but you understand I should have said that till the rate of cost to obtain the optimal duration, crash till the cost till the rate of, I should say here, rate of crashing is less than or equal to the overhead cost per day, okay, because you want to balance. So, this is the idea, and the moment you find that your cost of rate of crashing exceeds the overhead cost, then your total cost will also start going up. So, this is the idea, and so now let us just apply this ad hoc algorithm to this example, and I will try to show you some steps in detail, so that you can continue with the algorithm. So, you see here to shorten the duration of the project, following jobs can be crashed. So, these critical jobs, critical path is this. So, these are the 4 jobs on the critical path. So, you see 1, 2 can be crashed by 3 days, and the rate is 400 rupees per day. So, I have written down the rates here, and these are the days by which each activity can be crashed, right. But as I told you earlier, that job 1, 2 should be crashed by 2 days, because then the path 1, 3, 4, 6, 7 1, 3, 4, 6, 7, see that becomes also critical, because then the duration of the project, once I crash activity 1, 2, the project duration comes down to 24 days, and so this path also becomes critical. So, now I need to combine activities on the 2 critical paths, so that when I crash the 2 this set of jobs simultaneously, then the 2 critical paths will also get crashed, and so the project duration will come down, right. So, then here these are the combinations I have written down. If something is missing, you please check for yourself. So, anyway 1, 2 and 1, 3, see you can see that this is the second path 1, 3, 4, 6, 7. So, these activities are common, and these are the 2 these are the activities where the 2 paths differ. So, it can be 1, 2, 1, 3. If I crash both of these, then the total project duration will come down, because then both the paths will get shortened. Similarly, I take the other combination 1, 2 and 3, 4. Okay. So, 1, 2 and 3, 4 will help me to again reduce the project duration. Then 1, 3 and 2, 4 will also help me reduce the project duration, and then you see here 2, 4 and 3, 4. Yes, 2, 4 and 3, 4. So, I think this takes care of all possible combinations here, and then you see if I crash 4, 6, it is common to both the paths. So, then again the project duration comes down, and similarly 6, 7, because that is also common to both the paths, right. So, here I have written down the rates again, and so you can immediately see that this activity, this set of activities 1, 2 and 1, 3 can be crashed, and so here I can only crash it by 1 day, because 1, 2 now has left only 1 day slack, and this is what I meant, that somewhere you will have to note down that once you have crashed activity 1, 2 by 2 days, then 1 more day is left for it to be crashed, and so this pair cannot be crashed by more than 1 day, but our criteria is to go by the minimum rate, since we are looking for an optimum solution. So, therefore, this we will decide to crash by 1 day, and in that case the project duration will come down to 23 days, right. And then you can crash 6, 7 by 3 days, because 6, 7 is the next 1000 rupees rate of crashing, others are all higher than 1000. So, I will crash 6, 7 by 3 days, and then 4, 6 can be also crashed by 2 days, because this is 1, 2, 5, 0. All these numbers are less than see, and here once I decide to crash this one, this pair, then I cannot do this, because this is ruled out. Remember, 1, 2 has come to its last, the duration has been reduced to 3 days, I cannot reduce it further. So, then this is ruled out, and all the other 2 sets of activities are more than 3000. So, I will not consider them right now, since I am looking for an optimal pair, I am trying to get to an optimal solution. So, therefore, these are the 3 activities which I can crash, right. And so, by doing that, the project duration finally comes down to 18 days. So, both the paths have been reduced to 18 days, but in this case, in the process, now path 1, 2, 4, 5, 7, 1, 2, 4, 5. So, this also becomes, you see this here, this is 8, and this has come down to 3. So, 3 plus 7, 10, 10 plus 8, 18. So, this path also now has a duration of 18 days. So, you have 3 paths which are critical, right. So, now in that case you will have to again look at the combination of activities, which when reduced together will reduce the project duration. That means, will reduce the duration of all the 3 critical paths. So, here again 1, 3 and 2, 4, if you look at 1, 3 and 2, 4, yes, because they are this one is common to 1, 2, 4, 5, 7 also, right. So, therefore, I can crash 1, 3 and 2, 4, which will help me to reduce the duration of all the 3 critical paths. So, this way you can just verify for yourself that these are the 4 possibilities in which I can crash all the 3 critical paths, and so here again I will choose this one 4, 6, 4, 5, because this the cost of crashing is 2750, which is less than 3000 rupees. Your overhead cost is 3000 rupees per day. So, I can still crash this set of activities and improve my total cost of completing the project, right. So, therefore, this get crashed by 2 days, and so yeah, lack of space, maybe I can do it here. Yeah. So, now that means 16 days. 16 days is the project length, right. Once I crash this set of activities, my project length comes to 16 days. And now you see that after this, of course, yeah, this pair is valid, because 4, 6 can be reduced by how many days? 4, 6 can be reduced by 6 and 4. Oh, so no, 4, 6 can be 9 and 5. Okay, so the 4 days. So, therefore, I can also still further crash this, but which is the least one? Yeah, this is right. So, now that means 16 days will be your project length, which is your optimal, because after this I can crash this pair by 1 day, but the cost is 3250. That means, my cost is going to go up by 250 rupees. So, the moment your cost of reducing or completing the project and by crashing starts to go up, then that means you have reached the optimal duration here, and so you can further reduce the project duration to 15 days for example, by crashing this pair, right. And then if you want to do it further, for example, sometimes for the manager wants to know how far can you go, what is the minimum duration, even though the cost may go up, but you still want to know. So, like this is 15 days and then here you will want to crash this one by 2 days. So, that means it will come down to 13 days if you crash this set of activities 1 3 and 2 4. So, if you do this by 2 days, then I think this pair is out, because 2 4 is how much? For 2 4 the duration is only 2 days. You can crash the activity by 2 days only. So, you can either choose this pair or this pair, right. You can't have both. So, therefore, this is where you will stop, because 3500 is lower than 3750. So, you would still want to know what the minimum duration, and then corresponding cost should also be the smallest. So, therefore, if I decide to crash this pair, my duration will come down to 13 days. So, this is your minimum duration. This is your minimum duration, and after this, sit down and see for yourself that you cannot crash the activities any further, even if you want to increase the cost. So, this is your minimum duration, and 16 days is your optimum duration. So, essentially I have not made the actual cost computations, which you can do it along each of this, because you know by how much you are reducing the cost. So, you started with the initial cost of 31,000. Now, you can go on making the reduction in the cost, and you will come up to here, right, which means that, for example, this was 3 days, so 400. So, here you were making the reduction of 9,000 minus 1200, right, this many rupees. This was the reduction. 9,000 minus, so you will subtract this number from 31,000 to get the cost of crashing the project by 3 days, right. Similarly, when you chose this pair here and this was by 1 day, so then the reduction here would be 3,000 minus 900. So, that is the amount you will reduce from your total cost. So, please do this computation, and you will see that the cost keeps coming down, and then you will stop at 16 days, which will give you the optimum cost. So, here what we want to say is that it may not always be necessary that you to get the minimum duration, you have to crash every activity. That may not be feasible, and in fact, it will not reduce the project duration beyond 13 days. So, do not say that if you want to find out the minimum duration of the project, that you just add up the crash duration of each activity, and say that that will be the minimum duration. That means, you compute the you take the crash duration of each activity and then compute the longest path, that may not be equal to 13 days. I mean, that will not be the minimum duration. That is what I am trying to say. Okay. That is that may still not require each activity to be crashed, because after all you know that the project duration is determined by the critical path. So, essentially the activities which become critical, they have to be crashed, so that you get the minimum duration. So, some activities, for example, here 2.6 I do not think figures in any of the reduction thing. So, when you compute the minimum duration, your 2.6 continues to be because this path is 6, 11 and 11 for 15. So, at 13 the duration okay. No, you crash this to 3 days, and this activity 6, 7 we crash to how much? We crash 6, 7 by 3 days. Okay. So, that means here this is 1. So, this path will continue to be 3 plus 5, 8, 8 and 1, 9, right. So, you see 9 is much below 13. Therefore, there is no need for activity 2.6 to be crashed. I mean, this is one example I can give you right away, right. So, therefore, minimum duration does not mean that each activity of the project will be performed at its crash time. Only the activities which help to reduce the duration of the project, they have to be crashed. Okay. So, essentially now this is of course, you might say that lot of this thing can be programmed easily, but you can see what is happening from day to day. And so, essentially, and this is what a manager likes to know, that from day to day, if you are managing a project, how it is happening, how the cost is improving, what activities need to be crashed and so on. So, a nice ad hoc way which can be very easily implemented, but of course, you when the project is large, you might say that the number of, say for example, these combinations will go up. But again, you have simple rules to identify the combination of activities which will help to reduce the project duration and so on. So, therefore, what I am trying to say again, which I said in the beginning, is that in optimization you do not have to be strictly go by certain rules. You may have an algorithm to guide you, to take you towards a optimal solution, but in the process you can also exploit the structure and try to use some common sense and whatever information you can have to go to the optimal solution. This is the whole idea. Okay.